Okay, hi everyone. Thanks for coming to the Graphs and Matroids seminar. Today we have Carolyn Chun, who's at the US Naval Academy, who's going to be talking about lattice path matroids, lattice path polymatroids, and excluded minors. Go ahead, Carolyn.
Well, thanks everyone for joining me for this talk, and thanks so much, Shayla, for organizing. Shayla, did I pronounce your name correctly?
Yeah, that's right. Thanks.
Great. Okay. I'm going to view this in slideshow. So this talk is based on joint work with Joe Bonin and Tara Fife and was supported by, and this presentation mode has a mind of its own. It was supported by an Amos Simons collaboration grant. I'm going to talk about lattice path matroids, lattice path polymatroids, and excluded minors. So recently, over the last few years, I've been working a lot with Joe because of the vicinity to George Washington University from the Naval Academy, as well as Joe just being a great guy and a great researcher. And we worked with Tara on a few projects. And so this talk is, I feel like it's a few stops along the way of learning about different topics in matroid theory that Joe is interested in, and sort of combining a couple of them because he's interested in lattice path matroids and polymatroids. And so then we looked at, well, obviously the next thing would be lattice path polymatroids. So the traditional thing to look at for a matroid on slide 1 is the set of independence axioms. I'm not going to do that. Instead, I'm going to define a matroid by its rank function. So if you take a ground set together with a function and the function satisfies 3 axioms, then what you have is the rank function of a matroid. The 3 axioms are that the function should be non-negative and it's bounded above by the cardinality. So when I look at the rank of a subset of the ground set, you should never have the rank being higher than the cardinality of that subset. In particular, when you have a single element, its rank should either be 0 or 1. The second rule is that it should be non-decreasing. When you add elements to your set, you shouldn't lose rank. So thinking about that in terms of a matroid that's defined that you view as viewing a graph as a matroid or viewing a matrix as a matroid, adding elements doesn't decrease the number of the size of your independent sets. And submodularity, this is really where all the money is. When you have 2 sets and you take the rank of their union plus the rank of their intersection, that's bounded above by the sum of their ranks. So if your function meets these 3 conditions, then what you get is a matroid. And then if you look at the independent sets, which are the sets where the rank is equal to its cardinality, then you would get the something satisfying the 3 axioms for independent sets. But I used these axioms to define my matroid because they correspond to the polymatroid axioms for rank, with one difference. So you still have non-decreasing, you still have submodular, but for a polymatroid, you don't have this bound that the rank has to be bounded above by the cardinality. So in particular, if you have a single element in your polymatroid, it doesn't have to have rank 1. It could have rank 2, it could have rank 3, whatever you want. So that's going from matroids to polymatroids. So when I talk about matroids and I'm introducing matroids to people, usually I put points on a plane and we talk about, okay, which of these collections of points are independent, which are dependent. But for a polymatroid, putting elements in a plane, really the best I can do without having any sort of artistic inclination is putting points and lines. So I have points and lines here. So this is a polymatroid. Well, it's a geometric representation of a polymatroid where there's 6 elements in my ground set. My ground set is the elements 1 through 6 together with L1 and L2. And then the rank, when I look at subsets of the points, the rank is what you would expect for the matroid rank with points. And these lines, they each have rank 2. So every point has rank 1. If I want to look at the rank 2 sets Well, I could just take a single line together with any set of points that are on that line, and that will be a rank 2 set. Or I could take a collection of any 2 points. That would be a rank 2 set. And to get a rank 3 set, you can take a line together with a point off of that line, and that will span the whole plane. So you have a rank 3 set. So rank works in the same way as points in space in a matroid, but really what you do with lines is you can think of replacing this line L1 with 2 points that were freely placed on that line, and then all of your calculations work out the way that you would expect. A polymatroid has bigger element objects, and a k-polymatroid is a way that I can specify what type of polymatroid it is. It tells me what is an upper bound for the size of my single element objects. If I have all of my elements having rank less than 11, then I have a 10 polymatroid. So technically this is a 10 polymatroid because none of its elements have rank more than 11. So what is the lowest K that I could say this is a K polymatroid for? James Oxley says peace. Yeah, it's a 2 polymatroid. So drawing a 3 polymatroid on a plane. I've seen people do it really nicely, but I didn't attempt it. So some examples for polymatroids that researchers have been interested in are 1 polymatroids. Who cares about 1 polymatroids? Well, 1 polymatroid is, James likes it. But I can only see a few faces here, so some other people may be answering, but I'm looking at James and he indicates that he's interested in 1 polymatroids. That's because they are matroids. Here's another, actually, James, I think that you like this polymatroid as well. So when you look at a graph, there's lots of ways to get a matroid from a graph. And once you have a matroid, actually a matroid is a polymatroid, but you can get a polymatroid that's not a 1 polymatroid from a graph by taking as your ground set the edges, and then the rank is now the number of vertices incident with your set of edges. So I take the edges in my graph, and if I take a set of 3 edges that form a matching, then the rank of that set will be 6, for example, because those 3 edges are incident with 6 vertices. So what type of polymatroid is that? Is there a K that you can think of for it? I've taken on my advisor's annoying habit of asking questions during talks. So my advisor's penalty is that now he has to answer all the questions. James says 2, yep. So this is a 2 polymatroid. You can get a K polymatroid by taking K matroids all defined over the same ground set and adding together their rank functions. So that can give you a K polymatroid. And there's one other example that I'll put here, and this one's my favorite example. I actually it's something that I've worked on before, but it's called a deletion contraction polymatroid, and it has cool properties. But you basically start with a matroid and you pick an element in it and you contract it and you delete it. So you contract it and you take the rank function and then you add it to the rank function of M delete E. So now you have a 2 polymatroid that came from a matroid in a particular way, and they're called DC polymatroids. And I just think it's really cool because Deb Chun, my twin sister, worked on DC polymatroids. So now I want to work on CC polymatroids. I don't really know what those are, but I just think it's cool that DC worked on DC polymatroids. So minors behave the way that we expect, which is a good thing. As long as we expect the right thing. If we expect the right thing, then minors behave the way that we expect. So in graphs, minors behave in a really nice way. Graph minors are the first kinds of minors that I learned about. I didn't learn about matroid minors first. So starting with a graph, we can delete edges or we can contract edges. Any sequence of deletions and contractions gives us a minor. So the 3 bottom graphs are all minors of the top graph. And looking at the matroid of the graph, deletion doesn't change the size of your spanning trees. So your spanning trees in G are the same as your spanning trees in G delete 3, except for those spanning trees that included 3. So deleting an edge is really sort of a thing that really makes sense to me. You're just removing an object from consideration. Contraction is where your rank actually changes. So when I contract 1, now the size of my spanning trees goes down by 1 because I've projected onto a hyperplane in some sense. And I'll give an example of that in a minute. But in the same way that graph minors give me intuition and hopefully give you intuition about what's happening in a matroid, it also gives intuition for what's happening in the polymatroid. The only thing that's really different is when you contract objects that are of higher rank. So starting with my polymatroid, we can delete things. I'll delete 1 and L1. That's my new polymatroid. If I wanted to contract 1, then I take a hyperplane that's outside of, that does not include 1. So let me take L2. That's a hyperplane because it's got rank, well, the whole polymatroid has rank 3, L2 has rank 2. So now I'm going to project all the remaining elements onto L2. I've already got 2, 5, and 6 on L2. I'll project 4 onto 2 by drawing a line from 1 to 4 and just putting 4 on that point on L2 when I contract 1. Drawing a line from 1 to 3 means that I'll project 3 right on top of 2 to become a parallel pair. And L1, when I contract this point that's sitting on L1, L1 becomes a rank 1 object. It becomes a point that's also in parallel with 3 and 2. And the points 5 and 6 are already drawn there. So here's my polymatroid that I obtained by doing a contraction of a point. Contracting a line, this works in the same way like before, where you can think of the line as really being 2 points that are freely placed on the line. And instead of contracting the line all at once, you can think, well, let me pretend that L1 is just a green point here and a green point here. I'll contract those 1 by 1, and then I will get the minor. So even though we're operating on objects that have higher rank elements, we can actually resort to our intuition about 1 polymatroids. So if I contract the first invisible point, that puts 1, 2, 3, and the remaining invisible point all in parallel up here. It puts 4 onto this line, and 5 and 6 and L2 are unchanged. And then I contract the second invisible point, which has become parallel with 1, 2, 3. 1, 2, 3 then become loops. 5, 6, 4, and L2 all get compressed into a single point. So I go from a rank 3 polymatroid down to a rank 1 polymatroid. So I'm saying all these things about minors because I'm going to give an excluded minor characterization. And I just wanted to point out that intuition for minors works the same. I can see now that there's a chat and that Kevin answered 2 to 1 of the questions. And that's probably correct because like 2 is the answer to all the questions I asked. So just to put up the definitions for minors in terms of rank, for polymatroids, it's exactly what we expect based on your intuition from matroids. So your deletion doesn't change the rank of your objects or of your sets, and contraction can change the rank of your sets if the object that you're contracting is in the closure of the set that you're interested in, or if their ranks overlap, their spans overlap. So minors behave the way that we want, and there's intuition that we can grasp there. So then we can say, all right, well, now that we understand how polymatroid minors work, we can think about looking at a class of polymatroids and looking at its minors. So on the way to that, we're going to talk about lattice path matroids, which are a cool class of matroids that I like and that Joe has worked on, where you start with this grid and you think about walking, taking north and east steps from 0, 0 to 6, 4. So how many steps do you take all together? Well, you can go north, east, east, north, east, east. You can take 10 steps to get there. 4 of them will be north steps. 6 of them will be east steps. So how many paths are there? How many different paths are there to get from 0, 0 to 6, 4? Everybody.
10 choose 4.
Yeah, 10 choose 4. Thanks. I'm not sure who said that, but thanks. So 10 choose 4 different paths from 0, 0 to 6, 4. And that's sort of a hint as to what matroid this is representing. So this is a lattice path matroid. There's 10 choose 4 paths from 0, 0 to 6, 4. How does the path give us information about the matroid it's representing? But here's how we're going to do it. We take our paths, we look at them as sequences of n's and e's, and we think of them as being ordered from 1 to 10. Where do the n's fall? You're going to have 4 of them every time. Here they fall 1st, 4th, 7th, and 10th. So that tells me, okay, 1, 4, 7, 10. That's going to be recognized as a basis in my matroid. So we take all of the bases that can be constructed in like manner, and we get a matroid from this grid. So what matroid do we get here? I think, Charles, did you say something?
Is it U410?
Yeah.
No. Yeah.
Yes. Yeah. Yes. It's U410. Yeah. Oh. Yeah, U410. So any 4 elements in the set from 1 to 10 that you pick, I can pick those to be a basis. You want 1, 2, 3, 4. Well, I'll go north, 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 and then I'll go east. That's 1, 2, 3, 4. So you immediately deduce that lattice path matroids are not very interesting because they're all uniform. Well, here's the thing. Now we're going to bound the grid by 2 paths. So I have a path called Q and a path called P that now bound my grid. So now the basis 1, 1, 1, 1 is not a basis of my matroid. And I claim that there still is a matroid here. I haven't proved to you that there's a matroid here. But this is not U410. So how do we get the matroid here? What we do is we're going to be labeling our north steps, and that's going to give us a way to get a transversal matroid. So I really am just hitting all of Joe Bonan's favorite topics: lattice path matroids, transversal matroids. Lattice path matroids are really cool. It's a really cool class of matroids. They're closed under duality and minors in a way that's nice. And lattice path matroids have been studied by more people than just Joe, but these are the papers that were of interest to me when I was working with Joe on these. And in particular, I want to highlight this result about excluded minors. So Joe worked on an excluded minor characterization of these lattice path matroids. And I just think excluded minor characterizations are so cool because they're very elegant and concise. Sometimes it's difficult to say what a thing is. And so then to say what a thing isn't can be more enlightening. It's more helpful to see what is just barely outside of my class. So I just think I've always liked excluded minors characterizations, and there is an excluded minor characterization for lattice path matroids. So working with Joe on lattice path, who does lattice path matroids and polymatroids and excluded minors, the natural thing to do is to work on an excluded minor characterization for lattice path polymatroids. So back to lattice path matroids, a way to look at this matroid is as a transversal matroid where I get my sets from the rows. So now I'm going to take us as a set the labels here, where I've gotten these labels by putting the number of a step that step would be in a path. If I were to take this step in a path, this north step, it would have to be my first step. If I were to take this step in my path, it would have to be my second step. If I were to take this step in my path, it would have to be step number 6, whether I go north, north, east, 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 north, or whether I go east, 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 north, 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 it's step number 6. So I label all of my north steps in this way. And then I can take as set A1, the labels from row 1, and a step as set A2, I'll take the labels from the second row, and so on. And now what I can do is I can take the transversal matroid. I can forget about the lattice path representation, and I can just look at this bipartite graph and look for matchings there to find my independent sets. So it's the transversal matroid shown. So here, the rank of my set, I can figure out whatever set I'm interested in. If I'm interested in set 1, 2, 3, what I can do is find its rank by deleting the rest of the elements, the rest of these vertices on the right-hand side, and just looking at the largest matching I can find, which would, I guess, would be A1 to 1 and A2 to 2, because A3 and A4 don't meet this set. So that would have rank 2. We can see in the lattice path that makes sense, because the set 1, 2, 3, that only labels things in the first 2 rows. So I'm never going to get more than 2 north steps out of that. In particular, if I look at path, let me look at the path, a path that goes from 0, 0 to the 0.64 and make sure that it is incident with a matching. So for example, I've got 1, 2, east, 4, east, 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 8, east, east. So that tells me that 1, 2, 4, 8 should be incident with a matching. And it is. So that's a very convincing argument that these 2 matroids are equivalent. And this is for lattice path matroids, but it's not for lattice path polymatroids. But I like it. I think it's cool, so I include it in my talk. Now we're at lattice path polymatroids, and I would say that our work was independent of Schweig, but Schweig, and I'm probably pronouncing that incorrectly, worked on lattice path polymatroids and defined them. And so lattice path polymatroids can be defined on a lattice path in a similar way on a grid. And then they also have these corresponding bipartite graphs, but there's slight differences. So now I'm not labeling my north steps with what place they have in my path. I just label them all the same from that are if they're in the same column. So these are both 1, these are all 2, these are all 6. This is 7. And now what I do is I say the rank of my set is the number of rows that it meets. So if I want to look at the set 1, 7, well, that's going to have rank 1, 2, 3, because it meets rows 1, 2, and 4. So now I have a polymatroid on the ground set 1 through 7, which I indicate like this. That's just a set from 1 to 7, where the rank is the number of rows the set meets. So now if I want to forget about this and instead look at this bipartite graph where A1, that again is going to be my first row. A2 is going to be incident with all the elements in my second row, and so on. Now, if I want to know the rank of 1, 2, 3, I can delete 4, 5, 6, and 7, and then just see how many of these vertices on the left-hand side are not just isolated vertices. So the question is, how many of these row sets meet that set 1, 2, 3? And 1, 2, 3 is met by everything except for A4, so that will have a rank 3. And we can see, yeah, 1, 2, 3 does meet 3 rows. So in particular, this is a 3 polymatroid because the largest element has rank 3. So now we've finally gotten to lattice path polymatroids, and I think they're really cool. So in order to tell you about lattice path polymatroids, let me tell you something that's not a lattice path polymatroid. The Baumash matroid is the sort of quintessential matroid to look at for an example of something that is going to have bad behaviors. It's not going to behave the way that you want. It turns out that the Baumash 2 polymatroid is not a lattice path polymatroid, and it turns out it's going to not even be in this larger class of polymatroid that I'm going to discuss. So here I have 4 lines, A, B, C, and D. They're floating in space, and I've drawn these gray lines, which are not part of my polymatroid, just to indicate sort of how these lines are related to each other, how they're sitting in space. So lines A and B are not parallel. They do meet somewhere off of this figure. And so A and B are coplanar, so their rank is going to be 3. So the rank of each element is 2 because they're these lines, and the rank of AB is 3 because they're sitting in the same plane. AC is also going to have rank 3. BC has rank 3. In fact, every pair of lines has rank 3 except for AD. A and D are skew. So that's really what's going to present the problem, it turns out. So let me convince you that it's not lattice path by supposing that it is lattice path. So if it's lattice path, then we can get these 4 sets because the lattice height should be 4. That's my total rank. So I should be able to get 4 sets where my elements each meet some of these sets, and I can determine rank by seeing how many of these sets are met by my elements. So each element should meet exactly 2 of the sets because each element has rank 2. And I'm not going to think about, okay, what's going to be the order of my sets. I'm really going to just try to think about my sets. How can they be arranged? And we'll try to figure that out. I'm not going to try to put them in order from bottom row to top row. And that is an extra criterion. So without loss of generality, we say that A meets A1 and A2. Well, then D, because I know that the rank of AD is 4, and I know that D has to meet 2 sets, D has to meet sets A3 and A4. Element B meets A1 and A2 because the rank of AB is 3. So if B avoids this set, then the rank of AB would be 4. So B has to meet this set. Similarly, B has to meet this set. One of these 2 sets. So B has to meet A1 union A2 is what I should say. And B has to meet A3 union A4. up to switching the labels on A1 and A2 and switching the labels on A3 and A4, we may as well say that B meets A2 and A3. Well, C has to meet A1 or A2 because the rank of AC is 3. C has to meet A3 or A4, and C has to meet A2 or A3. C can't just be A2, can't meet A2 and A3. If C meets A2 and A3, then the rank of BC is 2. And that's not allowed. The rank of BC is 3. So that narrows it down. Either C meets A1 and A3, or it meets A2 and A4. And both of those give problems. So it's not lattice path, but actually this proof shows that you cannot even come up with sets that fit the description that, okay, however many sets my elements are in, that's its rank. So I can't even find these sets, these A sub I sets, let alone putting them in order so that they form a nice grid that's bounded above and below by 2 paths. So the fact that these don't have these, this doesn't have these sets means that the polymatroid is not Boolean. So I'm going to say something about Boolean now. So in the world of polymatroids, I promised something about Venn diagrams in the abstract of this talk, and everybody loves Venn diagrams. So in the universe of polymatroids, some of those polymatroids are Boolean. Clearly, the Vamos 2 polymatroid is outside of the class of Boolean polymatroids, but it is a polymatroid. And some Boolean polymatroids are lattice path. So this Venn diagram is just a concentric circles. It's a bullseye. So a Boolean polymatroid, it's a polymatroid where you can get this collection of sets from A1 up to AR, where the rank of your set X is the number of sets that X meets. It's kind of like what these rows were in my lattice path. So having a set of rows to tell me which, whatever X meets, however many rows it meets, that's my total rank. That would qualify for being Boolean. So this is an example of polymatroid that's Boolean and lattice path, because every lattice path matroid is Boolean. But if I added this edge in my bipartite graph, A1 to 7, if I say, all right, well, 7 is going to be in A1 as well. Now I have something that's Boolean because I've got these sets, A1 through A4, and that really does tell me the rank of my sets, collections in the ground set, but I don't have a lattice path picture anymore. I don't have a piece of grid that's bounded above and below by paths. So this is an example of a polymatroid that's Boolean, but it's not lattice path. And you could say, well, we're not really sure. It could be lattice path. Maybe we have to switch the order, like put 7 in front of 5, like move things around or move the rows around. And that's true. Sometimes you have a presentation that doesn't look lattice path, but you can find a lattice path presentation. But it turns out that this one doesn't have a lattice path presentation because there's a fundamental obstacle here. There is an excluded minor sitting there. So back to Boolean polymatroids. So Boolean polymatroids don't have to be lattice path, but they do have these sets, and these sets tell you information about the rank. And we've been looking from the left side of the graph sort of towards the right, but with Boolean polymatroids, where you can get this graph, this bipartite graph, you can actually start from the right and look to the left. And this is how we're going to get into the realm of Venn diagrams. Instead of thinking about my sets A1, A2, A3, and A4, I'm going to now think about 1 as having as its support rows 1 and 2, A1 and A2. I'll think about 2 as having as its support A1, A2, and A3. I think about 3 as having as its support A2, A1, A2, and A3 as well. And when I think about these supports, now I know how the elements are interacting with each other. And these, you get these supports in Boolean polymatroids. And it also gives you another way to view a Boolean polymatroid. I won't get into that when I'm giving my characterization, but it is another cool way to view a Boolean polymatroid. So instead of thinking of the elements as being that, being these vertical columns and being elements that show up in these sets, we think of each of these elements as being sets, we identify them with their supports. Then we can get the elements to be identified with the faces of a simplex with our vertices. So I'm going to do this as an example. I've got my Boolean polymatroid here. And on the right, I've got my 4 vertex simplex, because this is a rank 4 polymatroid. So I've got a 4 vertex simplex. And now I'm going to show how the elements correspond to faces in the simplex. And because it's a lattice path polymatroid, there's a particular sort of pattern to it. So 1 is just this line, A1, A2, and 2 is going to just be the face containing A1, A2, A3, and 3 and 4 are the same. 5 is the face containing A2, A3, A4. 6 is the same, and 7 is the face of the simplex, it's just A4. So looking at faces of the simplex, we can actually just represent the whole Boolean polymatroid in this way and try to find excluded minors by looking at these polymatroids, by looking at these simplicial complexes. And if you look at a simplex with k vertices and you learn something about it, that can tell you something potentially about Boolean polymatroids. That's sort of an aside about a cool way to view lattice path polymatroids. So back to the polymatroid that is Boolean, but not lattice path. So here I've got my non-grid sort of, and I've got my bipartite graph, but I didn't actually prove that this polymatroid is not lattice path. And that's what I'm going to do now. I'm going to focus on 3 elements in my polymatroid that are really causing the problem. And I think that you'll agree by the end of this that there's nothing we can do to get a lattice path presentation. So I've got elements 1, 5, and 7. I'm going to focus on them. And now I'm going to look at their supports. So I think of this support as being A1, A2. This one has support A2, A3, A4, and this one has support A1, A4. There's nothing common to all 3 supports. So on the right-hand side, I have this Venn diagram representing each of these elements where the middle part is gray because there's no element, there's nothing common to all 3. So this is empty. However, 1 and 5 do have something in common. 5 and 7 do have something in common. And 7 and 1 do have something in common. So I put a point into each of these areas. I don't specify whether or not there's a point in unique to the support of 1 or unique to the support of 5 or unique to the support of 7. All I really need is the information that I've said about these 4 areas. So once I know about these 4 areas, I can think, well, if I wanted to make a lattice path that represented these 3 elements, I would need the support for 1 to be whole. I need that to be one piece. Because when I break up the support like this, I lose my lattice path structure. So the support of 1, it has to meet has to meet 7 and 5. Well, in order to meet 7 and 5, but not meeting both at the same time, I need my lattice path to be 7 and then 1 and then 5. So you can think about a vertical step from a vertical step that is labeled 7, vertical line that's labeled 7, followed by a vertical line that's labeled 1, followed by a vertical line that's labeled 5. And there's nothing common to all three, but the vertical line that's labeled 5 has to go up and then come back around to sharing a point in common with 7. So it's like stair steps, but the top one has to circle around back to the bottom floor. And that's going to violate building our nice lattice path configuration. It doesn't matter what the actual rank of these elements are. So this isn't a precise polymatroid. It's not a unique polymatroid. It's a type of polymatroid. So the rank of 1 could be 10. The rank of 5 could be 10. The rank of 7 could be 20. It doesn't matter. If their supports conform to this Venn diagram, you're not going to be lattice path. And you're going to be of this type. We call it a Boolean 3 cycle. So it's a Boolean polymatroid. And because it's Boolean, I can represent it with this Venn diagram where I just look at their supports. And I call it a 3 cycle because I've got 3 elements and they kind of, I feel like they kind of form a cycle around this empty center. So 3 is not special. We can get Boolean R cycles. So you can think about the supports having something in common with each of their 2 neighbors, but nothing in common with any other supports. And then if the last support has something in common with the one before it and the first, then you're going to have another problem with trying to represent it as a lattice path. But it's a minimal sort of problem. If I delete the element represented by this support, then I can build my lattice path by having this be the bottom from the 0, 0 point up to whatever rank I need, and then have this be the next step. And starting from somewhere inside. Can you see where, can you actually see me when I'm making gestures? I'm not really sure. Yeah, okay. So you can see we could have this support being from 0, 0 up, and then the next support being from somewhere in the middle there up, and then the next support being from somewhere in the middle here, but not meeting the first support up. And you can go on and you get this sort of stair stepping effect. So you can represent it when you delete this element. So this is minimal. I haven't said anything about contraction. It turns out that contracting also gives you something that you can represent with a lattice path. But this may seem discouraging because I just told you there's infinitely many types of excluded minors for lattice path polymatroids. But that's not how I think about it. It seems like actually there's this bright side that we found this infinite family that we understand really well and we can draw in Venn diagrams. So maybe it's actually, we can characterize this as a win. I think that's something that I learned to do when I was working on the splitter theorem with James Oxley. Like anything that seems like we understand the structure somewhat, that's good. We take that as a win. So this is a Boolean end cycle. And just for fun, I drew a Boolean 6 cycle here. I mean, this is a 2 polymatroid example of a Boolean 6 cycle. The objects do not have to have rank 2, but this would be an example of, see, this is sitting in rank 6 space. So the red line meets the orange line, but the red line is skewed to the yellow line and the green line and the blue line, and it meets the purple line. So this is a polymatroid that is not lattice path, but it is Boolean, and it's a type of Boolean 6 cycle. But these could also be planes that have things in common, but are skewed to each other. I mean, you could have them be different types of ranks. But still, I think characterizing it as a Boolean 6 cycle, for me, that works. I like it. I say, yeah, we know what's going on. These are some more Venn diagrams because our whole proof was Venn diagrams. And when you can reduce something down to Venn diagrams, it's really satisfying. Like, I really feel like there's nothing that we've missed here, because a Venn diagram with 3 circles has 7 possible areas. And once you know what's going on in 7 possible areas, we know exactly what's going on in these 3 element guys. So I put these up just to show you some other problems that can arise besides these Boolean end cycles. So you can have a type of polymatroid, and I say type because I'm not going to specify what the ranks of the elements can be. They can be whatever you like, but if their supports interact in these ways, so if this is a 3-element polymatroid where the elements have something common to all 3 supports, and then each of them has something unique to their supports, and I'm not even going to specify whether these are empty or full, they can be whatever they like, you still cannot draw a lattice path representation of this Boolean polymatroid. This is going to give you a problem. T2 here, I put gray to indicate that this part of the Venn diagram is empty. So if you have something common to 3 of this all 3 supports, and something common to each of the intersections that is not common to the 3rd support, then you get another excluded minor type. So there's 4 types of Boolean polymatroids where each of them has 3 elements. And it turns out that those are really all the problems, except that there's 4 more. I didn't do the 4-element Venn diagrams. I find it difficult actually to even draw a 4-element Venn diagram. I sort of became an expert at it for a while when we were dealing with this. But there's 4 3-element excluded minor types. There's 4 4-element excluded minor types. And then there's this family of Boolean end cycles. And that is to characterize all the lattice path polymatroids that are Boolean. So either your excluded minor is one of these 2 cases, or your excluded minor is not Boolean. And you could say, well, it sounds like the work isn't done then, but I didn't tell you that, and I'm not sure how to pronounce his name either, Matroids, characterized the excluded minors for Boolean polymatroids. So starting from polymatroids, you can get to Boolean using Matroids, and then you can get from Boolean to the lattice path polymatroids by using our result. So every polymatroid is a lattice path polymatroid unless it has a minor that's either a Boolean end cycle, or that it's one of these 8 types, or is characterized by Matu in his paper. All right, that's my last slide. Thanks very much for your attention.
Thank you so much, Carolyn. That was great. Let's do a round of applause if everyone can please unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3. Excellent, thanks. And does anyone have any questions for Carolyn? If you do, you can unmute and go ahead. We don't usually have too many people talking over each other, so hopefully it'll work out.
I don't remember what Matus's excluded minors look like. Are they easy to describe?
No. I would say they're not easy to describe. And the paper is written using just a different perspective and sort of different language from ours. So, I mean, James, I do think it's something I should have a good handle on, but I don't, and it's not easy. It's not sort of easily grasped, I would say, but yeah.
The Boolean end cycle would actually be able to find the driver lat on a torus. So has anyone looked at lattice paths on surface of higher genus?
Mark, you cut out for a little bit. I think that you just said a Boolean end path is something, and then have we looked at paths on higher genus?
Yeah, I thought if you were on a torus, that end cycle wouldn't be a problem. You could make a lattice that just wrapped around the torus and itself again. So just wondering if the theory might be a little different on different surfaces.
Yeah, that's a good point. So why do we insist that our lattice be drawn on the plane as opposed to on a torus? If we have a torus, then my example for something that's not lattice path then becomes lattice path, because 7 just loops, just goes around to the back and comes out the bottom. So you then would, so if we, if you want to talk abstractly about surfaces, then you'll probably go over my head pretty quickly, but toruses, I think I can grasp. And I would say that you're going to pick up, if we're building the lattice on the torus, you'll pick up these end cycles, but you still retain these finite obstacles. I think that that's true. But maybe if you were on a projective plane, I mean, on a Klein bottle, maybe then you'd be able to do these. That's a fun question. I bet that it would be fun to try to answer that question.
Yeah, that was a good question. Are there any more? We probably have time for maybe one more if anyone has one.
Oh, for Venn diagrams, I did manage to draw 4 set Venn diagrams, but I can screen share in a second a picture of a 5 set Venn diagram from XKCD if people are interested about this.
Definitely. Well, maybe I'll end the recording there. And thank you again, Carolyn. And oh, well, this is good. Gotta have this on recording then. Oh my gosh.
Yeah, so they're like these oblong sort of shapes in order to get 5 of them that are all have this nice, like where all the shapes are the same, they're just rotations of each other, but you collect every possible intersection.
Have you played that board game Nitwit? Where
I haven't played that board game, and stop calling me a nitwit. I've never heard of nitwit.
in the game you make